Great. I'm seeing 12:01, so I'm going to go ahead and kick us off here. Thanks again for joining us, everybody. Today, our presentation is going to be covering code-compliant installation approaches under the 2021 IECC. Your presenters today are myself, Robert Schlorf, an energy engineer here at CDAC, and I'm joined by my colleague Ryan Siegel, who is a senior energy engineer here. Who we are, CDAC is an applied research program at the University of Illinois. Our mission is to empower organizations with practical solutions for climate, energy, and sustainability. What do? We assist buildings and communities in achieving energy efficiency, saving money, and becoming more sustainable. We'd like to thank our program sponsor, the Illinois EPA Office of Energy. Their support allows us to bring you this content in today's webinar. Today's webinar is approved for continuing education credits. We are an ICC preferred education provider, and we also offer AIA credits. If you provided your membership numbers with your registration for this webinar, we'll submit credits on your behalf. If you're attending this webinar with others, please follow up with an email or send Ryan and I a direct chat via the chat portal here to let us know who's watching with you, and we'll try to get you those certificates. This webinar is being recorded. If you miss anything or need a review, you can find this presentation and the slides on our website. Our energy training program also offers a hotline as well as an email for energy code related questions. You can send a quick email to get or send an email to get a written response back that may be able to be sent among multiple parties involved in a project. Or if you have a quick question, you can give us our call at our 800 number there. We do often prefer the email just to make sure that we have a written response and things are clear and there's no he said, she said, or misunderstandings over the phone. But of course, you're always welcome to call if you have a quick question. As I mentioned, our webinars are recorded and uploaded to our website at smartenergy.illinois.edu/energy code. Also on our website are self-paced on-demand training modules related to energy code content. These modules are free for anyone to take and offer CEUs with a passing grade of 70% on the final quiz. So if you find you want to dive further into the code or if you need further continuing education credits, check out those online modules that cover a variety of energy code topics. We also have smart tips on our website as well, short publications that talk about either building science or energy code related topics. This is a look at our schedule for this program year's presentations. Our last presentation was an in-person presentation covering code basics and the performance paths. Today, we're talking about code compliant installation. In the next few months, we'll be looking at passive house compliance and energy codes and resilience, as well as doing another in-person presentation covering code basics and the performance paths, as well as starting to look forward to the 2024 IECC for looks into what will be coming in terms of the code here in Illinois. Access to the Illinois Energy Conservation Code. So one of the best ways to access the code is online, which I'll show here in the next slide. But if you're looking for just general information on which code applies in the state, we try to keep our website updated with that information. So the current code within Illinois is the 2021 IECC with Illinois amendments. If you follow that link at the bottom of the slide here, that'll take you to our website that has a little bit more information as well as some other links. Here is a screenshot of the ICC online code version that provides access to the 2021 Illinois Energy Conservation Code. This is often how I and my colleagues here access the code online. It has a really handy table of contents along the left-hand side there and has a pretty robust search feature that allows you to navigate the code really easily. So this is a good way to access and get to the code without having a physical copy. Similarly, you can access the Chicago Energy Transformation Code, which is the current energy code that applies within the city of Chicago through the same format through the ICC website. It has the same table of contents and same easy search features. So if that code applies to your area or your projects, that is how you can access that code online. Similarly, we don't have a screenshot, but the ICC site does already have the 2024 IECC code up there, so you can access that code as well, just the same as the other two that I just mentioned if you're interested in looking forward at what requirements may be coming here in the future. Just a quick reminder that if you have any questions today, please use the Q&A feature at the bottom of your Zoom window. You can input questions in the chat, but we may or may not see those. So if you really want your question answered, make sure it gets in front of us. Try to use that Q&A tab, and we will try to get that answered or at least address it here within the presentation itself. And today our learning objectives are that by the end of this presentation, we hope that all of you can identify the building thermal envelope and insulation types, describe why requirements for continuous insulation avoid degradation and building health issues, describe appropriate insulation for different applications, and apply installation techniques and fastening methods for continuous insulation. All right, before we start this next section here, I believe we have a couple of poll questions here just to kind of level set and give us a little bit of information. So I'll go ahead and launch that here. So the first question is installation compliance a common sticking point for projects? So this could be projects that you see or projects that you're involved in. We have yes, no, sometimes, not applicable. And then the second question here, are you involved in or do you encounter projects using continuous insulation? Just trying to gather some general information to help us frame the conversation today. And something else we want to ask is that if anybody is answering the first question with a yes or a sometimes, and if you feel comfortable, please share us a little bit more information about what those sticking points might be. You can send something in the chat to everybody today. You can send a chat directly to Ryan and myself. You can even send us an email with this information. But it would be really helpful for us to have your perspectives as to what those sticking points might be so that we could potentially frame future content for you that might answer those questions. I can't promise we're going to solve those sticking points today in today's webinar, but if you provide us that information, we may be able to do that within the future. So if you feel comfortable, go ahead and share that or send it to us. Looks like almost everybody's answered here, but I'll give maybe one more minute and then close the poll. All right. Don't see any more movement, so I'm going to go ahead and kind of review our results here. All right, so for the first question, it looks like yes and sometimes are fairly common, but we also have some no's. So it seems like insulation is a sticking point for some, but not everyone. And then down below, there's actually quite a bit more projects using continuous insulation than I might have expected. So that's actually really good. We'll be talking a lot about continuous insulation within this presentation and the benefits of continuous insulation. So I'm glad to see that some of you are already familiar with continuous insulation. So at this point, I'm going to hand it off to Ryan to take us through the next section here, talking about the building thermal envelope.
All right. Well, thank you much, Robert. So in our building thermal envelope, wanting to make sure that we recognize and first define what is it that we're talking about today. So the building envelope, we're looking to separate what's inside from what's outside. There may be some spaces where we're trying to do some minimal conditioning, such as a sunroom or that, but the primary function here is separating what's inside from outside. And we do that through what's known as 4 primary control layers. So we're trying to make sure that we're controlling for water, air, thermal, and vapor. So thermal is what we're going to be focusing on today. And is part of this, again, trying to define what's inside from outside. So this can be roofs and or ceilings, walls, windows, floors, and so trying to define what is our boundary and envelope. So again, since we're talking about insulation, we're focusing on the thermal control layer, trying to minimize that heat flow into or out of the building. Now, recognizing, especially for residential buildings, the envelope is a big proportion of where that energy gets used for that. So part of the code is looking at for compliance, trying to standardize requirements. And the code, as you'll see, doesn't specify this is how you do things. It sets up thresholds and limitations for, you need to perform to this level. And so by having a code a single code document tries to bring some standardization to those requirements so that you don't end up with, in Illinois, we've got approximately 1,500 different permitting jurisdictions around the state of Illinois. So rather than having 1,500 different building codes to follow, having a single document or a document that has been perhaps slightly amended can greatly improve constructability uh, for buildings. So the goal here is to minimize heat loss or gain, recognizing during the summer we're trying to battle against heat gain from the heat outside going into our building. And obviously an objective here is to try to maintain stable indoor temperatures, preferably also indoor humidity, relatively speaking, uh, and trying to minimize our environmental impact for buildings. And so focusing on the envelope and the thermal insulation layer. So insulation is often done in respect to thermal resistance, or R value. That's what many people commonly know insulation values are. It's often the number that's stamped right on the insulation. Higher R values is greater resistance to heat flow. So R value is measuring resistance, whereas the U factor is measuring conductivity for that. So generally, this is known as the inverse of the R value, where lower is better. So if a perfect R value would be infinite, and a perfect U factor would be 0. So this is kind of correlating between each other. People may also notice that the tables in the code are provided for both R value and U factor. In the residential provisions, they now present the U factor first and the R value second for that. And with this, again, continuous insulation is a great way to reduce thermal bridging. So again, trying to reduce that thermal conductivity. And along with that, oftentimes insulation can help reduce air or vapor, uh, or can provide air or vapor management as well, depending on the type and quantity of insulation provided. And reducing the heating and cooling load for the building. So with this, you may notice in this building, trying to reduce that thermal bridging. Here we have an infrared thermal image, and we see that those bright, warm layers transmitting through the structural concrete columns and beams, whereas the windows are much cooler, and you're reflecting the coldness of outside here. So we're transmitting heat out of the building, and then allowing the heat in through the coldness in through the windows through this. So touching a little bit on the code requirements and continuous insulation. So part of this is understanding the definition of continuous insulation, and here we do note our definition out of the IECC, or the Illinois ECC, that the insulating material that is continuous across all structural members without thermal bridges other than fasteners and service openings. Again, we're trying to limit or minimize that thermal conduction, passing energy into or out of our buildings with that. And generally, this is a layer that can be installed either on the interior, that's perhaps less common. It may also be in the exterior, uh, or it can even be within an assembly. So we have seen places where you might have a double wall, and then they'll put the continuous insulation between the two layers of studs there for that. So again, recognizing that, wood commonly has an R value somewhere around 1 to 1.25 per inch of stud. So that means, a 2x6 is going to have, an insulation factor somewhere around 5, 6, 7-ish versus the insulation that's going to be between that may commonly be somewhere around, 20. So that stud provides a lot of thermal transmission from inside to outside. And so continuous insulation is seeking to address that bridge. So here calling out that the insulation layer, and we're indicating with a nice bold red line as far as where is this thermal envelope, trying to draw that layer of that thermal envelope, particularly focusing on where is that continuous, because that's where it's going to be the best performer, is where it's continuous rather than the cavity insulation. And you notice we're trying to wrap all the way around uh, that insulation layer. Of particular note as you're looking at or designing drawings or talking with your design professionals is making sure to pay particular attention anywhere this line bends. Any of those corners is likely to be where the difficult points are, or at least where the more difficult points are. Not going to say that continuous insulation is an easy thing to accomplish, but generally difficulties arise at joints and corners, where in the middle of a sheet of whatever the substance is, the middle of a sheet of plywood is generally not where I have a problem. It's going to be around that edge or a corner. So this is one particular assembly that we're showing here. This is another one. And so recognizing this can come in many different shapes and sizes. And so there's not one right way to do things in our region. So both of these would be appropriate for climate zones 4 and 5, such as we have here in Illinois. And you see here, this one, it's coming down the roof line, down the outside wall, and then transitions from the outside of the wall above grade to the inside of a below grade wall. So again, here we've got a couple of more corners in making sure that we are focusing on and in providing an adequate level of detail for all of these joints and convergences between the assemblies. So with this, there's a lot of different benefits for continuous insulation. We think of thermal performance. That's a common one because that's what we're measuring. So this is our R value or U factor that we're doing that. And by doing continuous insulation versus the cavity insulation is providing a more uniform insulation layer across that envelope. So rather than have these pockets every 16 or 24 inches on center that have a much reduced insulation value, having that continuous insulation across the entire uh, area can be of great benefit. So we think about when we put on our winter coat, we put a nice fluffy coat all the way around us in a generally even layer. Whereas rather than cavity insulation, we don't try to stuff our coat between our ribs to keep us warm. So having that nice consistency can be very beneficial. And that generally leads to reduced heating and cooling loads and can reduce not only the energy consumption, but it can also reduce capital costs from needing to install smaller heating and cooling equipment, smaller ductwork, and the like. Can also provide a lot of benefits as far as moisture and air control, depending on what the insulation is selected and how you install it. Making sure to seal any joints in that insulation can be of great benefit. And with that, by reducing air movement, that can reduce condensation risks because often air will transmit water, generally in the form of vapor, along with it. And if that vapor hits a cold surface, it can condense and lead to moisture issues and mold issues. We also deal with a lot of durability. So moisture brings with it durability issues. And so by managing that moisture, infiltration and exfiltration, allowing moisture when it does occur to get back out of the assembly can be very beneficial for the building's lifespan. And finally, if you have no other reason, okay, code compliance is a big piece of this as well. So we do expect more out of our buildings these days, and so making sure that we are able to achieve and get more out of it can be very beneficial with that. So it's a few different compliance methods as far as for commercial and residential. U-factor method can be found both in commercial and residential. These are both uh, prescriptive tables, and then there is a related UA trade-off method that's also found within the code. And then they do have an R value based method. So the U factor is something that the industry has been transitioning more and more towards because it allows for a lot more flexibility between continuous insulation and cavity insulation and your framing types and all of that. By having U factor, it just says, here's my level of performance, and however you wish to meet that, whatever blend of insulation types and methods you want to achieve that U factor, that works. The R value tables, we're seeing the industry perhaps move a little bit more away from this, but they're there to provide some default assembly types to say, okay, if you don't want to go through the calculations or the math to determine the specific U factor of an assembly, here are some assemblies that are deemed to comply and provide an approximate equivalent U factor for that. This UA trade-off, you might also begin to hear it being called the total thermal conductance value. So this is now being a new term being brought forward. And it's a little bit more descriptive as far as that UA trade-off, because we're really trying to evaluate what is the total conductance of the entire building shell for that. So U factor, as I alluded to, this allows for a lot more variation and flexibility as far as how much insulation, what is the method that you're going to use to install for that. And so it's just looking at what is the performance of the entire assembly, not just the individual insulation layers, but what's the whole assembly, recognizing that buildings are made up of assemblies. It's not just one layer of this or one layer of that, but oftentimes when you put two, three, four different layers onto things, that assembly is going to perform differently and perhaps better than the sum of its parts. So the tables in the code just calls out the maximum U factors for an assembly. So here we're going to look at the U factor method. So for our group zone, we're going to do an example here. So group climate zone 4 for group R with a metal frame building, the code calls for a maximum U factor of 0.064. And whatever assembly that you determine or work through that achieves that, we can work with that. So with that, if we look at the residential side of that U factor table, for a wood framed wall, this is common for perhaps low to medium rise residential, 8.045. Now, something that some of you may have picked up on is this is a lower U factor or a higher performance. Again, lower in U factor is better. So a higher performance for residential versus commercial, even though we're both looking at residential. And part of the reason is energy modeling has shown that for commercial buildings, these are medium to high rise buildings or those with commercial occupancies, the envelope is less of a factor in their overall performance. And so that's why they set for the residential provisions a higher performance target, recognizing that that envelope matters is more important in residential buildings. Not that it doesn't matter in commercial, but proportionally, it's a bigger factor. So, going to mention then we also have the R value tables. So this is another option for compliance as far as if you are using the prescriptive compliance path. And so it calls out in the table, here's how much cavity and here's how much continuous you need for that. You'll also see that they are separated in the tables, and they are just stating here is the insulation performance of the R value. So here again, we're going to look at climate zone 4 in a group R with a metal framed building this time for commercial construction. So for a commercial frame construction or commercial metal framed construction, group R, so residential occupancy within a commercial building, it's saying I need R13 cavity insulation, and then I need at least a 7.5 continuous. So 7.5 continuous, that's probably going to be somewhere on the order of inch to an inch and a half, depending on what type of insulation you select. It might even be 2 or 2.5, depending on some of the insulations we'll talk about. But with this, again, focusing more on that continuous insulation, because metal framed, a lot of thermal conduction through that. So they don't resist nearly as much as wood framed. Whereas if you see the wood framed right beside it, wood framed, it's calling for the same R13, but only a 3.8 continuous. So a substantial benefit in that direction. So here we're going to look at, again, wood framed walls for the R value tables. So this is where looking at it saying, okay, if you don't want to use a U factor and you don't want to use a performance path, you say, I want to use an R value, then this is where the code specifies. So I can either have anything from an R30 cavity insulation all the way to an R20 continuous. So there's nothing that says you have to put the insulation in the cavity. Uh, you know, putting an R20 continuous on the outside, that leaves a lot of room open for piping and ductwork or other things that might want to go in those walls. And by having that and that air control, you're also less likely to end up with frozen pipes too. So there may be some benefits of going just continuous and call it a day. Uh, so the UA trade-off I mentioned earlier briefly. So this is focusing on you can trade off within that thermal envelope, that red boundary that we had depicted earlier. You can trade off between various components. So we had one design recently come in, and they wanted to use less insulation in the walls, and they ended up specifying an R85 in the roof. And we said, okay, you can do that, and it's permissible, but that's you're going to struggle with trying to do that installation for that. So, but it does allow you to do some trade-offs. You know, walls, roofs or ceilings, floors, uh, windows. So various things there. Again, trying to keep the overall picture in balance with that, and recognizing a building is not just a wall or a roof, but it's a series of components all coming together. So we do call out there is performance-based compliance methods. So the total building performance is found in both the commercial and residential portions of the code. There is also a FIAS alternative. Presently, it's housed in R409. The commercial, if you do have projects out there that are wishing to do FIAS or PHI in the commercial provisions, you might ask your code official as far as making that acceptable as an alternative compliance method that is equal or better than the code under C10211. The code, the Illinois is presently looking to add FIAS and PHI as acceptable by default for the 2024 code cycle. So you're not having to ask for special permission for commercial buildings for that. So under total building performance, obviously we're focused on that energy modeling and mapping the entire building. So it's not only looking at the envelope, it's looking at, the HVAC and the lighting systems and allowing trade-offs between those systems. So if I build a tighter envelope, can I be a little bit more lax as far as the lighting performance? We do note here that the residential trade-offs are somewhat limited at this point in time for total building performance. And some of that is it focuses on ventilation and fan efficiency, along with air tightness, the envelope insulation levels, and energy recovery. So if you have energy recovery ventilation systems, that is a big boon for residential designs. You can take a lot of credit for having that, but having just a high efficiency furnace or cooling system doesn't get you benefits under the total building performance at this time. So ERI, this is strictly limited to residential construction. Again, if you do have some of these in a commercial setting, that would be very uncommon, but that might be an alternative compliance request through the code department. So ERI, this just assigns a numerical score on a scale from 0 to beyond 100. 100 is what is considered acceptable or a home built to the 2006 IECC. So here, what we're calling out is for construction, new home construction, homes with an ERI score of 54 in climate zone 4 or less, or 55 in climate zone 5 or less. Those are deemed to comply under ERI. So this is just a nice, easy numerical score from 0 to on up. So FIAS will touch a little bit on this. Again, this is one that it's not very common at this point in time, but it does make it a lot easier for compliance as far as from the code reviewers side, because these are third party, done by a third party. So having your list of features along with your pre-certification and then your final certification, and that takes care of compliance for FIAS or PHI. So they focus on these four main areas: radiation control, allowing that sun in when it's useful and trying to keep it out when it's not; air control, building that very tight house. Some of you might be familiar with, oftentimes these require air tightness levels of 0.6 ACH as compared to the code standard of 3.0. And then finally, thermal and moisture control, because we want these buildings to last. So making sure that we're doing proper moisture control with that. So with that, I've got a brief poll here. And that is, what are the four primary control layers of a building envelope? Air, floor, thermal, vapor, water, or windows? And number two, the UA trade-off path allows trades between all of the following except walls, windows, HVAC systems, or floors.
I do want to jump in and say thank you for everybody providing information within the chat. I'm seeing a lot of really good kind of long explanations of sticking points. We'll try to get to some of these today, but some of them we might touch on, but otherwise we might follow up, or like I said, we might use this information in the future. But I do appreciate everybody chipping in there.
And that's something that we're going to be touching on as far as the industry has been working to come up with additional solutions now that continuous insulation is becoming more and more used in the construction industry, trying to come up with some of the solutions to your problems. All right, looks like last couple of votes coming in. All right. So the four primary control layers of a building envelope. Air, yes. The floor, no. Thermal, yes. Vapor, yes. And water, yes. And windows, no. So looks like most everyone picked up on those four control layers. And then the UA trade-off. It is the HVAC system. It does not permit a trade-off between the building envelope and HVAC. So windows, walls, and floors are part of that. So HVAC is the correct answer to what is not part of it. So looks good. And with that, I'm going to turn it over to Robert.
All right. Thank you, Ryan. This next section here, we're going to talk about types of insulations, and I'm going to kind of try to breeze through this a little bit to keep us moving. We included this section within the presentation so that you can refer back to it. So if there's something that you missed, remember that the slides will be available on our website in the future, and there will be the recording, obviously, but the slides will be available for further review. So we're going to go ahead and get going here. So talking about the first type of insulation will be kind of blanket insulation or batten roll insulation. Most common type known is probably fiberglass, followed by maybe mineral wool, but there's also plastic fibers or even wood fibers that are coming to the market now. These are commonly for cavity assemblies. So cavity walls, cavity roof assemblies, cavity floor assemblies. That's most often where you see this type of insulation. However, you can use blanket type insulation as continuous insulation on the inside of foundation walls at times, or inside of masonry walls, but often on residential foundation walls. Pros of this insulation: it's very affordable, it's widely available, it's easy to install, but we have a little asterisk there because it does need to be installed with care. The con there requires precise installation to make sure that it is fit tightly within those stud bays, not allowing air leakage to easily move around those, or even air convection to happen within the stud bays. So we want that to fit really nicely within the stud bays. This type of installation generally does not prevent air movement. Some materials, such as fiberglass, can cause irritation. These slides will have a little bit of information on fastener types, but we will talk a little bit about those further on as well. But these slides will mention some common fastener types. Moving on here, we have a little table that kind of gives some of the common blanket type of insulations, the R values per inch, as well as talking about vapor permeability and air, and can these materials serve as an air barrier? In this case, vapor permeability class 3, that's the most vapor open of the three classes for vapor barriers. So as we can see, all of these blanket types of insulations are the most open in terms of vapor and cannot be used as air barriers. So keep that in mind when trying to put together an assembly, that these types of insulations can really only serve as the thermal insulation layer. Moving on to rigid board insulation. So we have probably one of the most common is polyisocyanurate or polyiso, often comes with a foil face on it. There are also phenolic foam boards, extruded polystyrene, XPS, as well as expanded polystyrene, EPS, mineral wool, fiberglass. So there's quite a variety. These can be used as most often as continuous insulation, but they can also be used on foundation walls. They can be used within insulated CMUs and ICFs. They can be used for walls, floors, roof ceilings, unvented roof assemblies, and even duct insulation. So excellent thermal resistance, especially when installed as continuous insulation. It does create that thermal break, as Ryan was talking about. They can be fire resistant, but not all materials are fire resistant in themselves. Sometimes it depends on a full assembly to gain fire resistance rating, often retain shape over time. These can be a little costly. They can be a little specialized depending on what the purpose you're using it for. And again, this is an insulation that needs precise fitting for the best performance. Just to touch on real quick, I mentioned these. So ICFs and insulated CMUs most typically use XPS, expanded EPS, sorry, EPS foams. So it's somewhat related to rigid foam boards. These are most often used for new construction, most often for foundation walls or above grade masonry walls, combines insulation and thermal mass, reduces thermal bridging in. It can be a very durable and fire resistant assembly as a whole assembly. These can be a little bit more expensive, requires more labor, and can be a little bit challenging within a retrofit situation. To give that table here for rigid board insulation, so we see polyisos up here at the top in terms of R value, while phenolic foam is a little bit higher than that, but phenolic foam is not super common from my understanding. And then we have kind of the R value kind of drops off as you go down here. There is a variance in these materials' ability to control vapor. So if you are thinking about using this material as part of your vapor control layer, keep in mind you may have to have a certain thickness here in terms of XPS. You may have to have a foil facing in terms of polyiso. So keep that in mind. And then using these materials as an air barrier, only some of these materials can be used as an air barrier. And then that also requires proper installation. Um, Moving on to loose fill and blown in insulation. So we're talking about cellulose, fiberglass, mineral wool again, sometimes recycled cotton or sheep's wool. These are really this type of insulation is really good for existing and new enclosed wall cavities. So um, often really good for retrofits where you aren't able to open up the entire wall, but maybe you can drill some holes in walls and then pump in loose fill insulation to add insulation to an existing wall assembly. These installations are typically eco-friendly, especially when we're talking about cellulose, which is essentially recycled newspaper or recycled paper products. There's some ability to control or limit air movement, but most often these materials are not considered air barriers. So it's not something you want to rely on in that sense. These installations can settle over time. They can create some dust while during install. There is some special equipment required, including this blower machine shown here in the picture. Again, not an air barrier. Uh, to show our table here. So the R values are fairly consistent across a lot of these materials. Again, vapor, these materials are very vapor open, and then none of these materials should be used as the air barrier. Some of them may limit air movement or cause some effect on air movement, but they should not be used as an air barrier. And then kind of a quick note here on product information. Some product information may say that these type of materials can be used as an air barrier or that they limit air movement. Just be really careful with those type of claims on product information. What we're looking for in terms of vapor control and air barrier control is, has that material been tested for that purpose? And is there a test result that shows, yes, this material is a class 2, class 1 vapor retarder, or can this material be used as an air barrier? There are tests to determine that. So just be careful when you're reading product information. Moving on here. So now we've gotten to spray foam and foamed in place. Typically, there's two main types of spray foam. Closed cell foam, which has a higher R value and can be more of a vapor and air barrier, or it has a little bit more control in terms of vapor and air control. And then open cell foam, which often has a lower R value, is usually vapor open, but does provide some air control. This is good for existing construction. It's good for new construction, masonry assemblies, enclosed cavities, encapsulated attics and/or ductwork. You can do all of this. One of the potential negatives of this is that stuff gets glued together, so it's a little bit harder to take back apart if you ever need to do that again, but it can be really good within those instances. As we have here, pros, excellent at air sealing and good moisture resistance, but we have those little asterisks there because it needs to be installed properly and at the right depths to make this insulation act in that way. It can be expensive, requires professionals to install, and there are some negative environmental impacts from these installations as well. So here showing our table, closed cell and open cell foam, air barriers. Closed cell can be an air barrier, but it must be installed at a minimum thickness of 1 inch. Open cell, some open cells can act as an air barrier at a minimum thickness of 3.75 inches. So we can see there's a big difference there in terms of minimum amount of foam that acts as an air barrier. So if this is part of your assembly design, just be careful and make sure that you are actually getting the amount of insulation that you need in terms of serving the purpose that you designed it to serve. Okay, kind of a quick run through of insulation types there. We're going to continue on with some practical applications for continuous insulation. So first, we want to talk a little bit about advanced framing with continuous insulation. So advanced framing is a framing technique that reduces overall lumber use and waste and optimizes materials and performance. So lumber is replaced with insulation wherever possible. This happens within headers. and at the rim joists occasionally, where you can pull that rim joist in and have exterior insulation on the outside. You're spacing studs at 24 inches rather than 26 inches. We're often using 2x6 studs as a minimum, single top plates, 2 stud corners, minimal jack studs, single headers, minimal cripple studs. So all of this is reducing overall lumber volume and allowing for more insulation. So those insulated cavities are getting bigger. The thermal bridges that Ryan talked about in the beginning, where that wood, that wood is an easier pathway for heat to flow in and out. In this instance, there's simply less wood for that to happen. So there are less instances of thermal bridging across an assembly using advanced framing. This is not necessary for continuous insulation, but advanced framing combined with continuous insulation makes for a very high performing assembly. And as Ryan mentioned earlier, so continuous insulation, one of the great benefits is that it helps us control condensation and mold growth. One of the ways that it does that is by helping keep the exterior sheathing layers warmer, so that even if we do get a little bit of air leakage from the inside hitting that exterior sheathing, it it the exterior insulation is keeping it warm enough to where condensation will not occur within that wall assembly and then lead to mold growth and degradation. So keeping that in mind as we keep moving forward here. Another option for exterior walls is called extended plate and beam walls. This construction uses 2x4 studs, vertical studs with 2x6 top and bottom plate extensions. You can also do this with 2x6s, 2x6 studs and 2x8 top and bottom plates. And we kind of see in the image here that what this does is it creates space for continuous insulation boards to be added, but still provides solid nailing at the top plates and bottom plates, and still uses full double rim boards here to provide extra nailing space or secure nailing space as well. So this isn't exactly continuous insulation by the definition within the code. However, it does give roughly about 95% coverage. So if you're looking at kind of wanting to use some continuous insulation, but not entirely sure about how to do it, this could be one method. And one way to account for this performance could be by going down the performance path, where you model the building, model it with the extended plate and beam system, and then that performance, that energy model will show the increased performance of this system over just a stick-built regular system. So if you don't go down the performance path and model the entire building, you may not be able to claim the additional boosts in performance that this offers by trying to go down just the prescriptive path. So keep in mind that when you're thinking about trying to use a new assembly or a new method, the performance path might allow you to take credit for what you're doing. Um, Moving on here, a couple more unconventional designs here for exterior walls, Mooney walls and T-studs. So the top image there is a Mooney wall. The bottom image is a wall framed with T-studs. We're not going to spend a lot of time here, but these create deeper insulation cavities, essentially increases overall wall R value and can help to reduce thermal bridging, comparable with various insulation types. And it can be a good base for exterior insulation as well. Now, this is unconventional and may require additional labor and training, but these walls do have pretty good increased performance over typical conventional exterior assemblies. So floor slabs and foundations. So the code tells us that we need to have the continuous insulation around the slab edges and below grade. Our graphic here is showing us 4 different methods that you could potentially do that. Now, keep in mind the graphic is showing some sub-slab insulation under the slab. That's only really required if you have a heated slab, but the 4 options that this graphic is showing us here are some of the typical ways of installing this floor slab foundation insulation. And one of the things we want to point out is that depending on where that insulation is installed, you can see by the red arrow here, depending on where that is, that could align with the next with the assembly, the exterior wall assembly above. Ideally, we want to align those insulation layers as much as possible. So depending on where you put your slab foundation insulation, that kind of guides you into where does your exterior wall insulation need to be, or how can I align these layers better to create that continuous big thick red line that Ryan showed us earlier on in this presentation. So you can put foundation and insulation horizontally as well. So that is permitted within the code, just to point that out there. Moving on here, so talking about some roof assemblies. So best practice is to insulate across the entire structure, not just within the cavities. This creates thermal breaks, as we've been talking about. You can, if you're doing this, use multiple insulation layers as shown in the top image there. Offset the seams so that the seams aren't lined up. This again helps to prevent any sort of thermal bridging that happens even between the panels. If you're making sure that those panel gaps aren't lined up, the overall assembly is improved. Low slope roofs commonly insulate above the roof deck and under the waterproofing membrane. Um, Sloped roofs can include spray foam beneath the decking, or board insulation, or loose fill over the rafters, or both. As Ryan said earlier, there is no one single correct answer for these assemblies. There are options, and then you have to decide on what your assemblies are going to be, and then show that those assemblies comply in terms of code compliance. And we'll talk a little bit more about that. But Brian mentioned the multiple ways to comply with the code: R value, U factor, UA trade-off, performance path. There are ways to account for all of these different assembly types within the code compliance pathways. An important note here at the bottom: specify raised heel trusses to avoid compressed insulation over the exterior walls. That right at the edge of the exterior walls there, that can be a really big thermal weak point. Raised heel trusses make sure that we have enough insulation there above the top plates to where there isn't really a thermal weak point. And if you do that, you can reduce overall roof attic insulation through R40221. R40222 provides something similar for low slope roofs without attics. So just keep that in mind, that that is an option. But again, we're trying to get that insulation to completely cover the exterior wall so that there's no weak point up there at the corner. A little bit more about roofs. In ventilated pitch roofs, you can install the insulation below the ventilation space to allow airflow between the ridge and the soffit. So here in this graphic, there's a little kind of yellowish line. That's the ventilation path within this assembly. That's actually within the insulated cavities themselves. So this assembly would require baffles at the eaves to prevent wind washing of that insulation. Furring or strapping can be added to create a ventilation space. So this can be done during new construction or even retrofit construction. This is a good way to, if a home is being retrofitted with a cathedral ceiling, a good way to ensure that that assembly meets code required insulation values is, rather than trying to shove all the insulation within the cavities, go ahead and modify the roof assembly as well to add additional exterior insulation. And then that additional exterior insulation can also include a ventilated gap above it. Ventilation, the decision to ventilate or not ventilate can include many factors, such as the roofing material above, the local climate, local wind loads, as well as local fire risks. If you're in an area with high wind loads or high risks of fire, you may not want a ventilated roof assembly. And then again, unventilated pitched roof here at the bottom. So this is showing insulation below the roof sheathing and air and water barriers. So that blue line there is the insulation, the continuous insulation layer within that assembly. Moving on to doors and windows. So one of the big things you can do with doors and windows is make sure you're specifying units that have integral thermal breaks that are already built in and designed into the frame. That reduces thermal bridging and the flow of heat inside and out. The important thing we want to do here is make sure that we're flashing appropriately to maintain continuity of the control layers. So we can see in that top image there, we've got the wall, the weather resistant barrier of the wall is coming over that buck that the window is installed on. And then talking about that, so there's two common methods for installing windows, especially with continued insulation. One of them is an Audi window, which is what these two images are showing, where there's typically some sort of pre-manufactured or site-built buck that extends the window rough opening out enough to where that once continuous insulation is installed, such as the lower photo there, that insulation layer is in line with the exterior of the window, and then siding can be added so that everything is in line. Um, Talking about an any window. So this is a detail of an any window. So in this case, rather than the insulation layer being aligned up with the continuous insulation on the outside, the window is pushed to the interior and the window is lined up with the interior insulation layer. So again, as I mentioned earlier, ideally we want these insulation layers to be lined up between walls, floors, foundations. As Ryan mentioned earlier, we want to make sure that that's a continuous red line drawn around the building. So Depending on the choice to do Audi or any windows really is a design choice, depending on how you want the windows to look. There are some benefits and cons to both. But again, you're thinking about how can I align these insulation layers, and the window is part of the thermal control layer. So it's important to think about that. Doors and entryways can be treated much like these windows here. So you're going to either be kind of putting it to the interior or the exterior. You might require a buck to help with your window as well, but that's one way to deal with doors and entryways. So a little bit about balconies and parapets here. So this is one instance where the performance path could really help some of those larger multifamily buildings. Install structural thermal break modules at balcony and parapet connections to limit thermal bridging through those facilities, through those assemblies. So often balconies attached to the exterior of the building have steel framing. That steel framing is often connected directly to the interior steel framing of the building. That's a direct thermal bridge that leads to heat transfer in and out. So products are coming to the market now that look like much like the central picture there, or the detail up in the top right, where you have some sort of high density foam assembly that allows for structural and rated by engineers structural connections that are compliant, but breaks that thermal bridge path. So if you're using these within a design, you can include these within a performance model and then get credit for them within that performance model. And then that might allow you to reduce the insulation requirements in other sections of your building, or potentially have some other trade-off that benefits your product. So your project. If you have a large multifamily building, rather than going down the prescriptive path, it might be worth considering the performance path and including elements such like this to take advantage of new materials and products on the market. So loading docks, this is a really, really tricky location. Unfortunately, there is no one right answer. It may be better to approach loading docks as a U factor approach rather than an R value approach. There are some products out there, such as blankets, that can help to prevent air leakage at these locations. Make sure that weather stripping and gaskets are installed. Use insulated leveler pits if possible. Ensure dock doors close flush with the exterior walls. If you can, push the loading dock outside and have it be outside the main thermal boundary of the building, the envelope of the building. There are also products such as the one shown on the right that kind of creates an insulated edge to a concrete slab that then maybe has either part metal or composite type materials that create a protective layer on the outside. More products will continue to be developed for this type of location. This is a very difficult location, but some creative approaches might apply here. And then remember, if you're using that product, such as shown on the right there, you could potentially take advantage of that, or take credit for that through the performance path if you model it into your performance model. Um, so there are ways to take advantage of different materials uses. I guess I will go ahead and launch our next poll question here, and while I'm doing that, I will talk about one of the questions that I saw come in. So here's our next poll question. Continuous insulation can be installed. The options are exterior, interior, within an assembly, all of the above, or none of the above. And then the second question is, continuous insulation increases the chances of condensation and mold growth, and your options are true or false. And what I was going to get back to was, I saw somebody bringing up the option of spray foam, and that spray foam should give us credit and allow us to use less R value because spray foam is tighter. There is a fact that spray foam can increase the air tightness of the building. One of the ways that you could take advantage of using spray foam within your assemblies is to go down the performance path, and through the performance path you can specify a air tightness level that is lower than the code minimums. And if using spray foam allows you to get to that lower air tightness level, then you are taking advantage of that benefit of spray foam. It may not directly, so you're using spray foam, you need less insulation in the walls. It's not that direct, but if you go through the performance path, using spray foam to make a tighter building envelope could lead to the ability to trade off in other assemblies. Going to go ahead and end the poll here. So it looks like the vast majority of everybody got the first question correct. All of the above in terms of exterior, interior, within an assembly, all of those are appropriate locations or potential locations for continuous insulation. And then second question, most of everybody got that one correct as well. Continuous insulation does not increase the chances of condensation and mold growth within an assembly. And at this point, I'm going to pass it off to Ryan to finish this off. I realize we've kind of hit our time limit here, but if you can, please stick with us and we'll try to finish this out.
Thank you. I do have just a couple of points here that we want to finish off with. And recognizing that continuous insulation, often where we struggle is fastening this, because, trying to go through that. So as far as when implementing continuous insulation, making sure that we've selected the insulation based on what we need as far as the insulation performance, moisture, and or fire resistance, as that's becoming a bigger topic now, is acknowledging that we need to make buildings more robust for that. So, and making sure that we've aligned that. So as far as how to do that, so addressing, making sure that we're checking, what points, edges, and penetrations, and the proper attachment length. Uh, one thing that we've encountered is the roofing industry has been using, you know, large quantities of continuous insulation for some time. So if you're struggling to find a fastener, that may be the place to look. It may not be with the rest of the fasteners. You might check your roofing aisle for that. So making sure that we're fastening far enough. So, and then are we flashing our window correctly? Making sure that we're maintaining a drainage plane so as we get our insulation and then our flashings towards the bottom of the window, installing our window and getting that flashing all the way around. So as part of that, the flashing becomes a bigger issue, particularly as we look at, do we put the window more towards the outside or the inside or the middle, as far as understanding where is that drainage plane and flashing that properly. So uh, there is a fair number of different fasteners to use, and so make sure that you're checking with whatever the manufacturer's instructions are to understand how it needs to be fastened, whether it's a nail, with a cap fastener, or if screws are permissible with washers, and some of this is how that might do over time. There are also some new products coming to market that we're seeing is shimming screws. So these are screws that, based on how you install them, can allow you to shift. Here in this picture, we see this strapping. So being able to shim and adjust the how far in these are driven, so you end up with a nice flush uh, plane to install your cladding to. So these are now also coming into the codes. So being aware as far as some of these newer products with that, and being able to adjust that so you don't end up with this nice wavy profile across your cladding because you used continuous insulation behind it. So adhesive base fastening. So this is something we're seeing coming to market. Not real common yet, but again, the roofing industry has used this a fair bit. So something to be aware of is, what does this do for to impact repairability? And if you do need to uh, get access to it, there's no longer a fastener to remove. It's now trying to remove that adhesive with that. So obviously the fortunate thing is, adhesives can substantially reduce thermal bridging as opposed to screws or nails, but you do have that impact of repairability later on. So clips, brackets, and systems. So again, these more and more are coming to market, and these can come in a range of materials. So going from aluminum and steel to better performing stainless steel, because that doesn't bridge as much, to now composites coming to market that can be designed to trade off between the structure, the loadability of it, and the bridging of it. So they can be designed for different attributes, and reaching out, again, looking at that U factor, reaching out to different product manufacturers and their installations, as far as, if I install it this way, what is the U factor that I achieve, or based on this spacing? The thing to be aware of is these are clips and brackets. This is not continuous Z channel, which we had seen some previous iterations seek to use continuous Z channel. Again, that's because you have such a long thermal bridge. That's not going to work as far as when the code is defining things. So again, as you're selecting your fasteners, making sure are they compatible with it? What is the local weather? Do you have high wind loads? What's the thermal bridging of that? Here, these are some look to be composite battens that are attached through the buildings. And again, looking for that fastener length. It's not uncommon to find some of these products, even those adjustable screws, to find those in 4 or 6 inch lengths out there in the industry. So, and then looking at the wall and making sure, have we prepared it properly? Did we verify that the trades were aligned based on the plan? When the plan was put together, it just determined an order in which holes would be made and then patched and things like that, so that making sure that the trades are in the right order. We understand things don't always happen in the planned order, but then identifying where were they not in the planned order and what is the impact or remedy or remediation that's needed for that. So again, making sure that we're sealing all the penetrations, because air, as alluded to in the question that Robert touched on earlier, air is a big piece of this. And so making sure that you don't get to your final certificate and not achieve the air tightness that you're seeking. So making sure that our openings are adjusted and in the proper alignment of various things, wherever if you are using a fluid applied flashing material, that's been applied properly in the right thickness, and that any bug screens that need to be installed are installed appropriately. So, and then cutting around all the different penetrations and openings and installing this. Again, this needs to be a tight fit, because we don't, all those gaps are potential paths for air and humidity to leak through with that. So if we do have multiple layers, it's not uncommon for continuous insulation to be done in multiple layers. So making sure to stagger those seams. So even if I have a seam in one layer, it hits a wall when it gets to the second layer. So you don't end up with a direct path all the way through. So, obviously needing to mark stud locations if you need to verify, you need to hit structure as you're installing all of this, and then finally putting your cladding on. So with that, I do have one final poll. I do appreciate everyone sticking with us and joining us today. If you do have questions about the presentation or other questions regarding the energy code that you have, feel free to reach out to us, energycode@illinois.edu, or our 800 number. So our poll questions are, first, guidance for minimum depth of fasteners through continuous insulation can be found where? In the mechanical code, the building code, the energy code, residential code, or none of the above. And second, continuous insulation may act as multiple envelope and control layers. True or false?
And as I
Uh,
mentioned in the chat here, this webinar is being recorded. I've inserted the link to our webinar page where you can go back to our recorded webinars in the past. This webinar will be up within a week or so, maybe a few days.
it looks like we've got poll in. All right, so the two places that you find it is in the building code and residential code. Those are kind of the two very similar codes as far as buildings go. That's where you find structural elements is building code and residential code. And continuous insulation can act as multiple envelope control layers. Yes, that is a true statement. So it looks like everyone picked up on that. So with that, I do appreciate everyone for joining with us today. And on behalf of Robert and myself, have a great afternoon. I do see a couple of questions that are here. Uh, Alan, sounds like yours is a fairly specific one regarding open and closed cell. I'd recommend go ahead and reach out to us at our email address, and we can follow up with you as far as the sequence of operations and things to be aware of for that. So,
I think Michael's question was referring to those wall sections we showed in the very beginning, so we might be able to send the link to that location to you, Michael, to give you a little bit of a closer look there.
all right. And let's see here, Robert, regarding how does spray foam insulation fall into continuous versus cavity? It depends on where it's installed and how it's installed. It may be continuous. Often it is installed as a cavity type insulation, but there may be means and methods to install it in such a way that it would be a continuous insulation for that.
I would say masonry assemblies, it's probably going to be more of a continuous application,
Yeah.
depending on the specifics, but
Let's see here. Then the question regarding zip system versus house wrap. Uh, this again, it depends on your installation method. Uh, they both can perform very well. Uh, House wrap can be a bit of a challenge because of how many hundreds of holes you end up puncturing in as part of the installation. Um, but either of them can perform very well. But it's that attention to detail that's going to matter. Uh, One benefit of a house wrap over a zip system is the quantity and length of seams that you have to deal with. Uh, but again, all the punctures is perhaps your bigger challenge with a house wrap system.
yeah, and I was just going to bring up that zip system could prevent you or could mean you go around the building one less time because you're installing sheathing and the weather barrier at the same time because those products are integral to each other. Now, you would have to go back around and deal with your seams or deal with those at the same time. So there's going to be trade-offs either way. But just keep in mind, one of the things with the zip system is that it is a system of products that are all meant to be used together. When they're all used together, the performance is really very good. But as Ryan said, you can get similar performance with a careful installation of house wrap. So just keep in mind that there's trade-offs and balances to both.
All right. Well, thanks again. Feel free to reach out to us, energycode@illinois.edu, and everyone have a great day.